We'll start in about a minute. Today we'll be in section 1110. This is the section on Taylor series and Maclaurin series. But first, we'll just do an aside. Consider how a power series representation of 1 over 1 minus x may be found in a different way than what we did before. Using long division, 1 over 1 minus x simply means 1 divided by 1 minus x. So in long division, if we divide 1 minus x into 1, 1 goes into 1 once, and then multiply 1 times the divisor. So 1 times 1 minus x is 1 minus x. And then we subtract. 1 minus 1 is 0. And 0 minus negative x is x. And 1 goes into x times, so we write plus x in the quotient. And then we multiply x times 1 minus x. X times 1 is x. And x times negative x is negative x squared, so we write minus x squared. And then we subtract. X minus x is 0. 0 minus negative x squared is x squared. 1 goes into x squared, positive x squared times, so we write plus x squared in the quotient. And then we continue this process forever. So we get 1 over 1 minus x equals 1 plus x squared plus x to the third, and so on. Of course, we do have only certain x values that work. This series converges only when x is between negative 1 and 1. So negative 1 is less than x, which is less than 1. If you're curious about other values, well, if x is 1, we get 1 divided by 0, which is undefined, so that's clearly not going to work. The other endpoint, negative 1, if you test x equals negative 1, then 1 over 1 minus negative 1 is 1 over 1 plus 1, or 1/2. And then replace every x with negative 1. We get 1 minus 1, and then negative 1 squared is positive 1, and so on. So this series clearly does not converge, which means that it diverges. Right? It just goes between 1 and 0, 1 and 0, and so on. So this series does not converge. Or you can say that it diverges. Anyway, that's just another way to think of finding a series for a rational expression. Okay, moving on. As we have seen, the power series representation of a basic rational function can be used to find power series representations of more complicated functions. One in particular, well, this was the main one, basically, that we used to find power series representations of more complicated functions. In this section, we will expand our knowledge by learning how to find power series representations of a few familiar functions, which can then be used to find power series representations of more complex functions. Okay, so here's a note to be aware of. There exist functions that do not have power series representations. But if, so that's the operative condition, if a function does have a power series representation, then that power series can be found. So we will begin by supposing that a function f can be represented by a power series at A. So what does that mean? If f of x is equal to a power series at A, then it's equal to the sum. The terms are c sub n times the binomial x minus a to the n, as n ranges from 0 to infinity. So if you multiply, or if you expand the sum, it looks like this: c sub 0 plus c sub 1 times the binomial x minus a plus c sub 2 times the binomial x minus a squared, and so on. And that's for all x values that are in the interval of convergence, whatever r happens to be. Okay, but note, if you evaluate f of x when x equals a, the only term that is non-zero is c sub 0. So the first term, c sub 0, is equal to f of a. Taking the derivative, the first derivative of f prime of x, well, if you take the derivative term by term, you're going to get c sub 1 plus 2 times c sub 2 times x minus a to the first, and so on. And when you evaluate the first derivative at a, the only number that remains is c sub 1. So f prime of a is equal to c sub 1. So keep in mind what we're doing. We're saying if a function f has a power series representation at a, then it has to have this form, and we're determining, well, the constant has to be f of a. The coefficient of the binomial to the first power has to be equal to f prime of a. The second derivative is the first derivative of the first derivative. So we just take the derivative of f prime of x term by term. And then when we evaluate the second derivative at a, we get f double prime of a equals 2 times c sub 2. But if we solve for c sub 2, we find that c sub 2, which is the coefficient of the x minus a to the second term, is f double prime of a divided by 2. Okay, then if we find the third derivative of f, we get this expression. And then if we evaluate the third derivative at x equals a, and then do the arithmetic, we find that c sub 3, which is the coefficient of the x minus a to the third term, is the third derivative of f evaluated at a divided by 3 times 2. Okay, if you continue this process, we find that the coefficients c sub n are the nth derivative of f evaluated at a divided by n factorial. This is a short version of the argument that's in the textbook on page 759, if you want to look at it in a little bit more detail from the textbook. Okay, a couple of notes before proceeding. One that we've already encountered, but just to make sure that it's clear. We have some notation for the nth derivative of the function f of x. The nth derivative of f of x is denoted this way. So there's a superscript. In parentheses, we have n. So this is just the nth derivative of the function f. So if 0 is in that set of parentheses, that just means we're talking about the original function. So that seems to make sense. The 0th derivative is just the function itself, if that's a word. We also adopt the convention that 0 factorial equals 1. And there's no harm in defining 0 factorial to be 1. It's evidently done for convenience. It just makes the formulas work more nicely if we say that 0 factorial equals 1. Okay, so that brings us to Theorem 5 on page 260. So remember, if a function f has a power series representation at x equals a, that is f of x equals this series. The terms are c sub n times x minus a to the n for the absolute value of x minus a less than r, the radius of convergence. Then the coefficients are given by c sub n equals the nth derivative of f evaluated at a divided by n factorial. So this theorem simply states what we observed on the previous page about the coefficients of the power series. Okay, but the power series in Theorem 5 is called the Taylor series of f at a. So more explicitly, the Taylor series of f at a is f of a plus the first derivative of f evaluated at a divided by 1 factorial times x minus a to the first plus the second derivative of f evaluated at a divided by 2 factorial times x minus a to the second, and so on. And then in sigma notation, so this, the nth derivative of f evaluated at a divided by n factorial, that is just the coefficient c sub n. And then the binomial x minus a to the nth power. Okay, there's another series, which is just a Taylor series at a equals 0. It's called the Maclaurin series. So the Maclaurin series is just the Taylor series when a is equal to 0. So it will be a little bit easier to just say Maclaurin series as opposed to the Taylor series at A equals 0. We'll automatically know that when we're dealing with a Maclaurin series that A is 0. Okay, so if you compare the Taylor series at A, where A could be any number, with the Taylor series at A equals 0, well, the only difference is instead of A, we're using 0. So the Maclaurin series of F is f of 0 plus the first derivative of f evaluated at 0 divided by 1 factorial times x plus the second derivative of f evaluated at 0 divided by 2 factorial times x to the second, and so on. Okay, so here's the formula for a Maclaurin series of a function f. So let's find the Maclaurin series for this function, f of x equals e to the x. So this might be the easiest Maclaurin series to find out of all Maclaurin series. So f of x is e to the x. What's the first derivative of f equal to? E to the x. The second derivative is e to the x. So on, the nth derivative of e to the x is e to the x. Okay, for the Maclaurin series, we want to evaluate each of those when x is 0. So e to the 0 is 1, so we can just cut to the chase. The nth derivative of f evaluated at 0 is e to the 0, which is 1, and this is for all values of n from 0 on. So this is for all n. Okay, so we can just write down, using this definition of the Maclaurin series. So f of 0 is 1, and then plus 1 divided by 1 factorial times x. So we'll just write, since 1 factorial is 1, we'll just write plus x. And then 1 divided by 2 factorial times x to the second. So 1 over 2 factorial times x to the second. And then plus 1 divided by 3 factorial times x to the third. And you get the picture. So we can write it. Well, it might be more convenient to write it 1 plus x squared over 2 factorial plus x to the third over 3 factorial, and so on. And so in sigma notation, from n equals 0 to infinity, we just write x to the n over n factorial. So you can see here it's evidently convenient to adopt 0 factorial equals 1. So that's it. That's the Maclaurin series for e to the x. Okay, so according to Theorem 5, if a function f has a power series representation at x equals a, then f of x is equal to the Taylor series. But how is it determined if a function is equal to its Taylor series? That's what we'll talk about next. But before answering that question, more definitions are needed. Remember that series have partial sums. So the nth partial sum of the Taylor series of a function f at a is denoted by t sub n of x. In earlier sections, we used capital S sub n to represent the nth partial sum of a series. But we're going to use capital T sub n of x to represent the nth degree Taylor polynomial of f at a. So that's what it is. The nth partial sum of the Taylor series of f at a is just a degree n polynomial, but in particular, it's called the nth degree Taylor polynomial of the function f at a. So t sub n of x then is just equal to the sum of the terms from the Taylor series where I ranges from 0 to n. So if we write out the terms, the first term is f of 0, then plus the first derivative, sorry, not f of 0, f of a, because this is the Taylor polynomial of f at a. So f of a plus the first derivative evaluated at a times x minus a to the first, plus the second derivative of f evaluated at a divided by 2 factorial times x minus a to the second. And then the last term that I didn't leave room for me to write. I'll write it down here. The last term of the degree n Taylor polynomial is the nth derivative of f evaluated at a divided by n factorial times x minus a to the n. Okay, so in general, there are n plus 1 terms in the Taylor polynomial t sub n. Okay, let f be a function whose nth degree Taylor polynomial at a is t sub n of x. So I'm going to make this claim. There exists a function capital R sub n of x such that f of x equals t sub n of x plus R sub n of x. So let's consider whether this statement is valid or not. What if a function f of x is not equal to its Taylor series? Then how could this possibly be true? Well, it's really quite easy. Maybe it's already obvious to you. Even if a function f of x does not equal its Taylor series, where n goes to infinity, well, if t sub n of x is the nth degree Taylor polynomial for the function f, we can always find another function that, if necessary, can negate whatever terms in the Taylor polynomial is necessary, and then write all of the appropriate terms so that when you add them up, you still get f of x. Okay, so we'll assume that's obvious. The function capital R sub n of x is called the remainder of the Taylor series of f at A. So what must be true if a function f is equal to its Taylor series at A? What's that?
The remainder equals 0.
Yeah, the remainder has to go to 0. But earlier this semester, remember from section 11.2, we defined a partial sum S sub n of a series well, we can start at 0 or 1, whatever, but it's just the sum of the first n plus 1 terms of this series. And if that series converges, then the limit of the sequence of partial sums has to be equal to the full series. Oops, here we're going from n equals 0 to infinity. And I really flubbed that one up. This should be a sub I. So the series converges if the limit of the sequence of partial sums converges to some number s. So the same idea works here. So if f is equal to its Taylor series, at A, then f of x has to be equal to the limit of the Taylor polynomials t sub n of x. But since f of x is equal to t sub n of x plus the remainder r sub n of x, it must be that the limit of the remainder as n approaches infinity is 0. Hey, does that seem to make sense? Sort of. Okay, we'll let the theorems make that claim. So the theorem 8, if f of x equals t sub n of x plus r sub n of x, where t sub n is the nth degree Taylor polynomial of f at x equals a, and if the limit of the remainder r sub n of x equals 0 for the absolute value of x minus a less than the interval of, or the radius of convergence, then f is equal to the sum of its Taylor series on that interval. Okay, but the next question is how to determine when the limit of the remainder r sub n of x equals 0. And for that, we have the Taylor's inequality. This is on page 762. So this is basically a theorem, this Taylor's inequality. If the absolute value of the n plus first derivative of f evaluated at x is less than or equal to m for values of x such that the absolute value of x minus a is less than or equal to d, then the remainder r sub n of x of the Taylor series satisfies the inequality. The absolute value of r sub n of x is less than or equal to m divided by n plus 1 factorial times x minus a to the n plus first, n plus 1, for the absolute value of x minus a less than or equal to d. Okay, that's the statement of the inequality. Okay, so we will do a little bit here. Show that if the absolute value of r sub n of x is less than or equal to m divided by n plus 1 factorial times x minus a, the absolute value of x minus a to the n plus 1, for the absolute value of x minus a less than or equal to d. Show that the limit of the absolute value of r sub n of x is equal to 0. And if we could show that the limit of the absolute value of r sub n of x is 0, then we can conclude that the limit of r sub n of x itself is also equal to 0. Okay, so to do that, find the interval of convergence of the infinite series, the absolute value of x minus a to the n over n factorial as n ranges from 0 to infinity. So we know how to do that. If we apply the ratio test, then the absolute value of a sub n plus 1 over a sub n. So we're using this as our a sub n. And we get this expression, the absolute value of x minus a to the n plus 1 over n plus 1 factorial times n factorial over the absolute value of x minus a to the n. When we simplify, we get the absolute value of x minus a over n plus 1. And then we take the limit by letting n go to infinity. And for all x, this limit is 0. But in particular, it's going to be true for the values of x that satisfy this inequality. Okay, so what we learned earlier in chapter 11, if a series converges, in this case, this series converges for all real numbers x, then the limit of the sequence is equal to 0. So this was one of our earlier theorems in chapter 11, if you remember. Okay, so if we consider the limit as n approaches infinity of the absolute value of r sub n of x, from up here in the Taylor's inequality, So replace the absolute value of r sub n of x with m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. So this is just m times the limit as n approaches infinity of the absolute value of x minus a to the n plus 1 over n plus 1 factorial. Okay, so if you believe what we showed earlier, the only difference between what we showed earlier is that instead of n and n factorial, we have n plus 1 and n plus 1 factorial. So this limit should be 0. Since the limit of the absolute value of r sub n of x is 0, then the limit of the terms themselves is 0. Okay. So the limit of x to the n over n factorial as n approaches infinity that's equal to 0 for all real numbers x. This is just a special case of this one up here that we concluded must be 0, since the corresponding series related to that converges. Okay, let's move on. Show that the function f of x equals e to the x is equal to its Maclaurin series. Okay, so the n plus first derivative of f of x is equal to e to the x. So for the absolute value of x less than or equal to d, where d is any positive number, we have the absolute value of the n plus first derivative of f evaluated at x is less than or equal to what number if the absolute value of x is less than or equal to d? What do you think? Well, since e to the x is an increasing function, And if the maximum absolute value of x is d, and the nth derivative of f evaluated at x is e to the x, the maximum value of this has to be e to the d. So in the Taylor's inequality, e to the d is equal to the m. Okay, so by Taylor's inequality, we have the absolute value of the remainder is less than or equal to e to the d over n plus 1 factorial times x to the n plus 1. Okay, so when we take the limit, we're going to get 0. So the limit of the absolute value of r sub n of x is just the limit of a constant e to the d over n plus 1 factorial times the absolute value of x to the n plus 1. Well, for each fixed value of x, this limit is 0. Okay, so since the limit of r sub n of x is 0, we conclude that e to the x is equal to its Maclaurin series. So we can write it out. Conclude that e to the x is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial, and so on. It's equal to its Maclaurin series. Okay, let's see if we can find the Maclaurin series for f of x equals cosine of x. This will be a little bit more involved than finding the Maclaurin series for e to the x. So let's start making a list. F of x equals cosine of x. The first derivative of f of x is negative sine of x. The second derivative, what's the second derivative of f?
Negative cosine.
Yeah, negative cosine of x. So the third derivative positive sine of x. So let's write one more. The fourth derivative of f of x is back to cosine of x again. Okay, so for the Maclaurin series, we want to evaluate each one of those when x is 0. So f of 0 is cosine of 0, which is 1. F prime of 0, negative sine of 0 is 0. The second derivative of f evaluated at 0, negative cosine of 0 is -1. The third derivative of f evaluated at 0 is sine of 0, which is 0. And then the fourth derivative, evaluated at 0, we're back to 1 again. Okay, so the Maclaurin series, well, we have f of 0, that's 1. 1 over 0 factorial times x to the 0. I guess I can write that out. 1 over 0 times, not 0, 0 factorial. 0 factorial is 1. So 1 over 0 factorial times x to the 0. And then plus 0 over 1 factorial times x to the first. Plus -1 over 2 factorial times x to the second, plus 0 over 3 factorial times x to the third, plus 1 over 4 factorial times x to the fourth, and so on. So what do we get? We get 1 and then 0. The next one is minus x squared over 2 factorial. This term is 0, so the next one is plus x to the fourth over 4 factorial. So do you think you know what the next term is, even though we haven't accounted for it? Yeah, minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial, and so on. So the sigma notation then, so n equals 0 to infinity. So it's an alternating series. So -1 to the n. And the terms? X to the 2n over the 2n factorial. So that's it. Okay, now let's find the Maclaurin series for f of x equals sine of x. Well, I didn't leave much space, but we don't need much space. All we have to do is what? Yeah, since the derivative of cosine of x is sine of x, we'll just take the derivative of the Maclaurin series for cosine of x, and that will give us the Maclaurin series for sine of x. Oh, but I made a mistake here. The derivative of cosine of x is negative sine of x. So that's sort of an important detail. So negative sine of x, it turns out that the Maclaurin series for cosine and sine, or the Maclaurin series for each is equal to the function. So I am not incorrect by writing negative sine of x, which is going to be the derivative of the Maclaurin series for cosine of x. So the derivative of 1 is 0, and then we get negative x. When you take the derivative of x squared over 2 factorial, you're just going to be left with x. And then plus the derivative of x to the 4th over 4 factorial is going to be x to the 3rd over 3 factorial because the 4's cancel. And then minus x to the 5th over 5 factorial. And then plus x to the 7th over 7 factorial. And so on. But for sine of x, we multiply everything on both sides by -1. So the Maclaurin series for sine of x is x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So what's the sigma notation? Well, this will be the last thing we do here. So n equals, well, we can start it at 0 or 1. Let's start it at 1. So what are the terms? So -1 to the n minus 1, and so x to the 2n minus 1 over 2n minus 1 factorial. Yeah, I think that works. Okay, so we're out of time. We'll do more of the Taylor and Maclaurin series tomorrow.